Thank you. Hello, everyone. I'm going to talk about some simulations with a regional climate model using a groundwater scheme over South America. So our region of interest is the La Plata Basin over the south of South America. This region covers parts of 5 countries in South America, including Brazil and parts of Argentina. It is the second largest river system in South America after the Amazon. This is one of the most densely populated areas in the continent, so it is very important from a social point of view. Some of the most powerful storms on Earth take place in this region, and this, for the land-atmosphere interactions community, this is a very interesting region because here several studies have shown a very strong coupling between the land and the atmosphere. So we have 2 questions. The first one, from a regional climate model simulations point of view, is what is the role of adding groundwater to the simulation of soil moisture and evapotranspiration in a land surface model? And then the second question is, what is the consequent effect of the groundwater on the simulation of precipitation? And these are 2 separate questions because we use 2 different methods to answer each question. So the first question, what's the effect of adding a groundwater component to land surface models? In general, and from a global and regional point of view, groundwater can move in the lateral direction from high topography to the valleys. And if you have complex topography, you can have motion of movement of water from the hills to the valleys. And this creates a mosaic on the distribution of the depth of the groundwater. And in some parts of the world, the groundwater can be very close to the surface. And according to some estimates, over some regions in South America, including the Amazon and La Plata Basin, the groundwater can be as close to the surface as 25 centimeters. So between 25 centimeters and 2.5 meters. And again, I insist, this is from a regional point of view. And this can have an impact on the simulation of the evolution of soil moisture fields and evapotranspiration in climate models, both in general, in global climate models and in regional climate models. So some previous studies have found that when in the land surface model, they add the groundwater below the soil layers, the unsaturated soil layers, and they compare this kind of model simulations to simulations without the groundwater at all. They found an increase in the simulated soil moisture over parts of the Amazon. And here the blue colors indicate that there is a net increase in the moisture simulated by the model with the groundwater component. And the thing is that this change, this positive change, is larger in those regions where the groundwater is closer to the surface. In those regions, people would say that the water table, that's the depth to the groundwater, is shallower. So in regions where the water table is shallower, there is a largest increase in the simulated soil moisture in this type of models. And once you have more soil moisture in the root zone, you potentially can have more evapotranspiration. But the evapotranspiration not only depends on the availability of moisture in the soil, but also on atmospheric conditions. So in this study, the authors found that from the increase in soil moisture, there was also an increase in the simulated evapotranspiration, but only over the south of the domain, over the south of the Amazon, where the atmosphere can still hold more evapotranspiration from radiation and vapor pressure deficit. So the effects of including this kind of components in land surface models are not homogeneous over the world. They depend on the topography, because topography controls this lateral movement of groundwater, and they depend on atmospheric conditions, because atmospheric conditions control whether you can actually have more ET or you're going to have the same ET as with the old model. So with that in mind, we ran a couple of simulations, but over the south of the continent, and this is our model domain. You can see here a portion of the Amazon basin, the southern half, And then here we have the La Plata River Basin, which is almost totally contained in this domain. We have two simulations, one simulation with the groundwater scheme and the other simulation without the groundwater scheme. We call this type of simulation free drainage, because once the water from the soil reaches the bottom layer of the soil column in the model, it just leaves the domain and it's allocated to the runoff that the model is simulating. And then what we did was to use the same atmospheric conditions for both simulations. These kind of simulations are called offline simulations because you just simulate the land surface part and then the atmosphere is the same. You use, for example, realistic conditions of the atmosphere. And this kind and the input from the atmosphere to the model includes precipitation, low-level winds, moisture, temperature, and radiation, and also pressure. So with this configuration, we ran two simulations for a period of 10 years. And with this grid size, actually, we explored the effect of the grid size. And I'm going to show you later what happened. And this is what some of the results that we got. First, we checked the water table depth simulated by this model. You can see here the green colors and the yellow colors indicate that the water table depth can be in the range between 2 and maybe 5 meters in some regions of the La Plata Basin and the Amazon. This is deeper than what is suggested by observations, but this is what currently the model is simulating. And then in other regions where you see here the orange colors and red colors, the water table is really deep into the soil. In those regions, we don't expect to have a really large impact of the groundwater scheme on the simulation of soil moisture and ET. And in this map, what you can see is the change in soil moisture when we have the groundwater scheme compared to the old model without the groundwater scheme. And here the blue colors show that with the groundwater scheme, we have more moisture over regions of the La Plata Basin and some parts of the Amazon. And locally, in some points, the increase can be as high as 20% of the default values in the old model. So this is a significant fraction of the moisture simulated by the older model. The thing is that this result and what I'm going to present in the next slides are conservative estimates of the effect of the groundwater, because here what we have is deep groundwater, deep water tables. And if we were using realistic estimates of the water table, we will expect the effects to be even larger. So although these estimates these changes are interesting, they can be conservative. And now that we have more soil moisture in these regions, we also found more ET in these regions, especially in the south of the domain, where I told you there is a strong coupling between the land and the atmosphere. So here, the atmospheric conditions are favorable for using that extra moisture from the soil to produce more evapotranspiration. However, you can see that here, over the western part of the southern Amazon basin, we had more moisture in the soil from the groundwater scheme, but that moisture is not being used by the model to simulate more ET, because basically here, the atmosphere is not providing the conditions for extracting that extra moisture. And the increase in the ET can be as large as 40% over some parts of the domain. So that's a significant fraction. Then what we did was to explore the effect of the grid size, of the lateral grid size in the model domain. Because as I told you before, if you have the lateral movement of groundwater depends on the topography. And if you have a grid size that is really large compared to the topographic gradients, you can have this kind of slopes, for example, in your model domain. But if you use a smaller grid size, you can start to see some local valleys. And in those valleys, you're going to have this convergence of groundwater. And if you have this convergence, you can expect more soil moisture in these very localized regions and maybe more ET. In this loop, what we are seeing is the extra moisture from the groundwater scheme, the extra ET from the groundwater scheme, when we ran simulations with a grid size of 20 kilometers. And you can see that the effects are mostly located over the south and then a little bit over the Amazon. But something interesting happens when you run the simulation with a smaller grid size, and you start to see more blue here in the region of the Amazon. And this is happening because in this region now we are seeing, the model is actually seeing these topographic gradients, these small valleys, and in these regions we are seeing more moisture and more ET from the lateral movement of the groundwater. So what's interesting to note here is that first, if you add the groundwater scheme, even at this grid size, which is typical of regional climate models, you're going to see an impact in some regions, especially, for example, in this case, in the south of South America. And second, if you are going to high resolution, you can actually see some of these effects in important regions like the Amazon. And this has been interesting to other studies because these could support the ET, that is the extra ET that is observed during the dry season, and that was described in some other studies this morning here. So in summary, we found more soil moisture in the root zone when we used the groundwater scheme over some regions, especially in those regions where the water table is shallow. And then we found that over some of these regions, there was also an increase on ET, and this depended on the atmospheric conditions. And then at high resolution, we see an effect of the groundwater scheme on those regions with small topographic gradients, and this happens over the Amazon. And remember that all this happens when you compare two simulations that have exactly the same atmosphere. And these results, you can find details of these results in this paper. So now that we know what happens with the land surface, with the storage of moisture and with the flux of moisture from the surface, with the same atmosphere, we want to know what's going to happen with the atmosphere, what's going to be the reaction and the interaction with the atmosphere once you have more ET. Some previous studies suggest that over South America, if you run a simulation with a regional climate model, if you start the simulation with less soil moisture, you're going to see less precipitation. And this light gray color shows that there is less precipitation over most of the South America when this group started the simulation with less soil moisture in the regional climate model. And something kind of the opposite happened when they started the simulation with more soil moisture. But this is not trivial, this is not straightforward. For example, over some regions, over the western of the Amazon, when they started the simulation with more soil moisture, actually they had less precipitation. And this can happen because once you have more soil moisture, the surface can cool a little bit and then can produce a more stable atmosphere. So we have to pay attention to this combination of more moisture, but also we need the instability, the atmospheric instability to have more precipitation. So this is not trivial, and that's why you need to do the math. Having more moisture not necessarily means that in the soil, not necessarily means that you're going to have more precipitation. And this was from a modeling point of view. Here, from using data closer to the observations, this group found that, especially during this early rainy season in the south of the continent, they found that when they observed more soil moisture in October, they also found usually more precipitation during November. And this happens over the regions that have the red colors here, over the south of the continent, in these two graphs. They were using a sophisticated measure to measure that coupling. And they found something similar between the soil moisture in November and December, and something analogous for the negative anomalies. So at least to the south of the domain, we could expect that having more soil moisture, we can have more precipitation. But again, this is not trivial, and here the Western Amazon shows that this is not always the case. So what we did to do the math was to use the weather research and forecasting tool, the WRF model, to run a couple of simulations. One with the groundwater scheme and the full atmosphere, and one without the groundwater scheme. Each simulation was for 4 years, and here are some of the details. We ran a continuous simulation during these 4 years. But here I'm going to show only results for the season, October, November, December, which is the early rainy season of that over that region. This is our model domain. This is slightly larger than the previous model domain, because now we have the atmosphere, and you can see here the La Plata Basin and a large part of the Amazon Basin. So first we had to check that actually coupling with the atmosphere, what was the effect of the groundwater scheme on ET and soil moisture once you coupled with the atmosphere. And again, this is not trivial. If you couple the atmosphere, let's go back a little bit. If you couple the atmosphere to these simulations, something can happen. Well, you have several options, but one of the things that can happen is that if you start with the groundwater, you can have more soil moisture and then more ET, but once you have more ET, you can have more specific humidity here in the lower layers, so that you decrease the vapor pressure deficit, and once that happens, maybe the atmosphere is not going to allow more ET, so the ET can dampen. So that's one possible result. So it is not trivial that with the full atmosphere, you're still going to see the extra ET from the groundwater. Maybe the atmosphere is going to block that extra ET. But what we found is that the atmosphere over the south of the continent still allows for that extra ET from the groundwater. And this is the extra soil moisture, and here we have the extra ET, and again, we have extra soil moisture over the south and over the Amazon, but the extra ET is observed only over the south of the domain. So now, what happened with the lower layers in the atmosphere? Here we see the change in the temperature, in the near surface temperature, when you add the groundwater scheme. And what happens is that the temperature actually decreases when you add the groundwater scheme. And this is happening because the solar energy, the solar radiation is being used to produce more evaporation and not to warm the surface. So the temperature decreases. So there is a cooling. And then because you have more ET, you also see an increase, in this case, a slight increase in the specific humidity near the surface. Now, here we have vertical profiles of the relative humidity and the moist static energy for two regions over the south of the domain. And what we see is that in the lower layers in the atmosphere, from the surface to 800 hectopascals, the groundwater simulation produces a slight increase in relative humidity and moist static energy over both regions. Here we have two competing mechanisms. We have more moisture from the groundwater, but we also have this decrease in temperature. And you need both the moisture and the temperature to actually have instability to produce vertical motion in the atmosphere. So you have more moisture, but lower temperatures, but still we observed a net increase in the moist static energy, which will be associated with an increase in convection. And you can see this in this plot, this graph. This map shows the increase in the convective available potential energy over the domain, and this is coming from including the groundwater. So the red colors and the yellow colors mean that we saw a net increase in the convective instability over parts of the domain, and this in turn produced an increase in the convective precipitation from the model, in this case the WRF model. And also, over the south of the domain, we also saw this increase in the large-scale precipitation that the model is able to simulate. And this is related to the increase in specific humidity in the lower layers in the atmosphere. So what we saw was that over those regions where we saw an increase, a change, positive change in the evapotranspiration, due to the groundwater scheme, we saw a net increase in precipitation, and here this map shows that the fractional increase can be as large as 30% over some parts of the south of the continent. So in this sense, this could be important for that part of the domain. And here what we have is the temporal evolution of the regional averages of the extra ET and the extra precipitation that comes when you use the groundwater scheme. So the first thing to note here is that the change in evapotranspiration is always positive. You see here only positive values, and this means that when you use the groundwater scheme, you always get more ET. You never get less ET over that part of the domain. And what's interesting here is also that the extra ET, which is the gray, represented by the gray bars, the extra precipitation is a significant fraction of the extra ET. And when you do the math, you find that this extra precipitation is not coming only because you have more moisture in the atmosphere to have, let's say, bigger drops or something like that. It's because that extra moisture is also increasing the instability in the atmosphere. So you have both effects, more moisture and a more unstable atmosphere. Then when you take a look to the fractional increase in ET and precipitation during over this region and over the whole period of simulation, the average increase in ET is 13%, and in precipitation we have an extra of 10%. So is this important? Is this even relevant to reality? It seems that this is relevant. Here what we have are a couple of maps that show the biases in the simulation of temperature and precipitation by a suite of regional climate models compared to a suite of observations. And this red spot here means that there is a warm bias in the models compared to observations right over the La Plata Basin. And here we see the colors here are a little bit confusing, but here this blue means that there is a dry bias in the regional climate models that were used in this study compared to observations. And the thing is that when we include the groundwater, we see a cooling, a decrease in the temperatures. So this seems to be like a fix in the right direction, a fix that maybe these models would need. And we see extra precipitation. So this could alleviate the dry bias the regional climate models are seeing over that region. So in this sense, these changes induced by the groundwater scheme seem to be relevant to fixing some of the biases of the regional climate models over the region. So in summary, what we found is that including the groundwater scheme increased the land surface, modified the land surface fluxes, increasing ET, increasing precipitation, and producing a net cooling. And the effects are stronger over the La Plata region because of the strong coupling with the atmosphere. And then the stronger effects are observed during the early rainy season. So this is not happening all the time, but there is a time in the year when this can have an effect. In this sense, this is interesting when you compare to the studies that were mentioned this morning, when people are concerned about the date of the onset of the monsoon over Brazil. Here we see that the groundwater is affecting specifically a season during the year, but over the south of the continent. You can see the details of this study in this paper, where you can find some details about the model configuration and some other results. So finally, some ongoing research. Because of the effects of this groundwater scheme on the simulation of land surface fluxes, we are now interested in what's the effect of not only groundwater, but also what people call dynamic vegetation schemes in representing, in simulating evapotranspiration and soil moisture, but over the Amazon, and specifically during late and early onsets of the South American monsoon. This new scheme, what's of interest to us of this scheme is that it tries to represent how plants respond to drought and to an increase in temperature. So in that sense, if you have drought, maybe the way plants contribute to transpiration is going to change in this kind of models. So we want to combine both kind of schemes to see what's the internal variability of these fluxes and how they behave, especially during late and early onsets of the South American monsoon. These are some preliminary results. Here, what we see is the change in evapotranspiration when we add only the groundwater component. This is analogous to what we saw before. Only adding the groundwater component, we see an increase in evapotranspiration, especially over the south of the domain, indicated here by the blue colors, and a little bit over the Amazon, the southern Amazon basin. But when you add the dynamic vegetation scheme, you see actually a decrease in the simulated evapotranspiration over some parts of the domain. Specifically during the dry season, this is July. It's not visible here, but this is July. And during the dry season, this additional scheme reduces ET. This could preserve soil moisture for later during the year, maybe preserving more soil moisture to be used close to the onset of the South American monsoon. And this happens, these are results, these are the mean results for 10-year-long simulations. And the interesting thing is that there is also some interannual variability. Here, these time series show the extra ET from the groundwater scheme when you use only the groundwater scheme, computed over different regions. And the thing is that with the groundwater scheme, as we saw earlier, you always get a net positive change in ET. And these changes are not constant from one year to the other and are not constant during the year. So there is some internal variability. And here we see the time series when you combine the groundwater and the dynamic vegetation scheme. And you see that sometimes you get more ET, positive values here, but sometimes you get less ET, the negative values here. And these troughs here are changed from one year to the other. So you get this interannual variability that could be related to changes in the date of the onset of the monsoon. Well, that's something that we would like to explore. So, okay, so that's what I wanted to show you. I would like to acknowledge the co-authors of these two works, and of course, the people that provides the funding for this. And thank you. Now, if you have any questions.
Thanks so much for very nice presentation. I have a question. When you introduce the groundwater, does that improve the flood plan simulation, like representation in the model?
Oh, okay. Well, that's a very common question. The thing is that in previous studies over the Amazon, using this scheme, Miguel Macho and Professor Fan, they used both a groundwater scheme and also a scheme to represent flooding over that region. We are not using that kind of representation of what happens when you have flooding over the domain. And this could be very important, especially over the south of the domain, over La Plata Basin. So at this point, this is not included in the domain, in the simulations. And what we expect is that when you include that component, plus a more realistic representation of the water table, you are going to still see a larger effect on ET. And that's going to change definitely the runoff, the simulated runoff, especially the runoff by the model. But that's still not included in the current model, in OMP at least.